morning, fellow mathematicians, welcome back to another video. I'm really excited this time, okay? This is going to mark the start of a mini-series I've waited on doing for 1.5 years by now, and I finally planned everything out. This series is going to be called Complex Numbers but Different. Oh, this sounds really exciting. Complex numbers, our best friends. Physics people love them. Applied philosophy students love them. Everyone loves complex numbers. But this time I'm going to present complex numbers to you from scratch in a completely different way. It's going to be really exciting. What do you need for the series? Well, all you really need is this first video right here. So watch it till the end, seriously. The result that we are going to discover today is extremely fundamental, and also it requires little to non-linear algebra knowledge. If you do not have any linear algebra knowledge, okay, that's the main tool here, watch till the end. I'm going to propose something there at the end, okay? And even while filming this video, I'm going to explain a bit of linear algebra to you, okay? So do not worry, even if you've never heard of linear algebra, bear with me. It's going to make perfect sense, everything right here. So, you know, there are numbers, and there are algebra people who thought about, well, what's the solution to x minus 1 being equal to 0? Well, that's just x being equal to 1. Or what's the solution to, for example, x over 2 being equal to 1? Okay? Algebra people thought about things like this. Many different number systems have been discovered or invented. It really depends on your point of view. And one of those came into play a few hundred years ago, okay? One of those number systems. It's the most important number system by far that we have, okay? There's a whole theory about complex numbers. Now, what was the big question that everyone was asking a few hundred years back? Well, if we have x squared plus 1 being equal to 0, then what is the value of x? I mean, if you have the prerequisite knowledge about complex numbers, it's going to be easy, plus minus I, okay? But we don't want this right here. We are going to derive everything using real methods only in linear algebra. Now, if we were to solve for our boy x right here, well, that would imply that x is thus equal to plus or minus the square root of -1. And if you have never heard about complex numbers, this doesn't really make any sense to you, okay? What is this right here? In school they tell you, well, it doesn't exist, there is no 0 there on this interval, coolio, okay? Just really don't think about it too much. But this right here is a serious question, and if we can solve this right here, then it opens the doors for so many branches of mathematics, and even the whole singular theory about complex numbers in this case. Now, I would like to approach this problem right here differently, okay? I would like to make use of linear algebra, like I said before. For this, we are going to take a look at just a simple 2x2 matrix A right here, okay? We are going to call it A. Capital letters mean matrices. And for the moment, it's just going to consist of, well, those entries, A, B, C, D, where all of those entries are out of the real numbers, okay? And we would like to use A as being our x right here. So what we want to do right here, we want to find a solution to this problem. A squared being equal to, well, in this case, -1, okay? 1 is something we don't really have right here when we are dealing with matrices, so we have to deal with the identity matrix in 2 dimensions, okay? That's supposed to be a weird squiggly 1 right here. I'm terribly sorry. Okay, this is our main problem right here. This is just this problem being translated into matrices. We don't want to use square roots right here, okay? Matrices are real operators. It's a bit squiddly fiddly to use square roots on matrices, okay? If you've never done function analysis, it really doesn't make too much sense to you, okay? This is the first thing. But complex numbers have a few ambiguities with them, okay? And that's about the plus and minus square root of -1, okay? This thing right here, that's a bit, okay? It provides 2 solutions to the same problem, meaning I would like to put another restriction on our A, which is extremely important, and it's only going to make sense later in the game when we are talking about geometric interpretations of complex numbers. Okay, we want the transpose of our A to be equal to the inverse matrix of A. This right here is more formally known as being an orthogonal matrix. Okay, A, we want it to be orthogonal. And do not worry, I'm going to explain everything about those matrices one after another. Okay, so we want to deal with this thing right here. Now we want to find out the entries of A, B, C, D, because if we can find out the entries, well, that's cool. We know the form of our matrix then. Well, let us go ahead and get started. So, what does it mean to square A and arrive at negative the identity matrix in 2 dimensions? Well, here's the first part. A squared is nothing but A times A, okay? It's just like with real numbers, for example. I'm going to write everything out. That's going to result in ABCD times ABCD. And now matrix multiplication. You can do this nice and formally using sums and then multiplication of the entries and so on and so forth. But I'm going to show you a little mnemonic device, okay, such that you can remember it for all times and for all matrices you are going to ever multiply together, okay? It's going to be nice and spastic and it's so much fun, and if I explain this to first years, it's so much fun watching them do this, okay, in the exercises and also when they have the exams, okay, it's so much fun. Now what you want to do is, we want to take this first column right here and put it onto the first line, multiplying those entries together and then adding all of those together, okay? We are going to do this, put it on here, and then we are going to do what I just said. We are going to have A squared plus B times C. Okay, next up, for the next entry up here, we are going to do the same spiel, okay? We are going to have AB plus and then BD. Let us move on, next one. Now we are going to take this column right here and put it onto the second row, okay? Just like this, okay? It's nice and spastic, it's so much fun. Now we are going to have AC plus C times D. And for the last one, BC plus D squared. Okay, this doesn't look too bad at the moment, okay? If we are dealing with matrices, 2 matrices are exactly equal if and only if the dimensions are equal. So 2 by 2 and 2 by 2, that's once again a 2 by 2 matrix. Okay, this is how matrix multiplication works. If you take a look at the dimensions of the corresponding matrices being multiplied together. And also, if and only if their entries are equal. Meaning if we take a look at negative the identity matrix. What does the identity matrix look like? Well, it's nothing but 1s on the main diagonal and 0s everywhere else, okay? That's just the identity matrix. And here's another little matter of fact. If we have a scalar, okay, something out of the real numbers, times a matrix, it's defined pointwise, just like with vectors, for example. Meaning we can multiply each and every entry by the scalar out here. Meaning, we now have this system of equation, which tells us that, for example, A squared plus BC is equal to -1. And we also have, for example, B and then A plus D being equal to 0, and with the other ones too. Okay, this is just how matrices work, and you can just identify the entries one after another and solve systems of equations, and this is the pure beauty of linear algebra, okay? It's just so nice. You always deal with some systems of equations and you can work with those. It's so cool. Okay, linear algebra is trivial but cool. Now, if we just simply were to take a look at this problem, I tried it out for myself, you are probably going to arrive at infinitely many solutions to this problem right here. This is why we had to introduce this other one right here, this other condition. This is a really important one. A transpose being equal to the inverse of A. Now, we are going to use this fact right here. At first, let us say something about the transpose of A. Okay, what does the transpose even look like? Well, the transpose in itself is really easy to grasp, okay? If we have A transpose, it's just that we keep our main diagonal how it is, and we are treating it like a mirror, meaning those are going to get reflected. Our transpose matrix is thus nothing but A, C, B, and D. That's the transpose, and it's really easy to handle, to be honest. Now, this is also equal to our inverse matrix. Not talking about the inverse in itself now, this is going to be a part later in the game. Now, one cool thing about the inverse matrix. It's just like you have it with real numbers, okay? Now, if we have the real number 3, for example, then the multiplicative inverse of this thing is 1/3, okay? 1/3. And thus, they are going to cancel out to be 1. It's the same spiel here. If we have A times the inverse of A, or the other way around, inverse times the matrix in itself, it's going to result in the identity matrix in set dimensions. Now, we can make use of this fact to finally solve this thing right here, because now we are going to apply the inverse matrix, or should we say the transpose, okay, it's an orthogonal matrix, to both sides of the equation. Let us see what this is going to result in. Now we are going to have A times the inverse, I'm going to denote it as the transpose, being equal to negative the identity matrix in 2 dimensions, times yet again the transpose. And at the moment it really does matter when it comes to matrices and the theory of operators, where we apply this operator to, okay? A transpose, we are applying it to the right. We don't know yet if our operators are going to commute with all the elements in there. They do. It's really cool. Complex numbers do commute, okay? But we don't know this for now. Now, like I said before, we are applying our inverse, our transpose, to our matrix in itself. Meaning this thing right here is going to result in the identity matrix. One more cool thing is if we have 1 times 3, for example, okay, this is just going to result in the thing itself. So if you only have 1 apple, then you only have 1 apple, okay, as always. Meaning on this side we also have the identity matrix times the transpose is going to result in negative our transpose. Meaning, overall, what are we going to get? This line right here is equivalent to saying now that we have A times this thing right here, okay? A times our identity is just A in itself, is thus equal to negative the transpose. Meaning, negative the transpose is thus nothing but, oh, I have the transpose up here, I'm terribly sorry. Just -1 multiplied into here, to each and every entry. Negative A, negative C, negative B, and negative D. This is just how it is. Now, we can actually continue because we know that 2 matrices are exactly equal if and only if their entries and dimensions are equal. Meaning we also know that this thing right here is equal to our boy A. Now, what we are going to get is that we have that this is A, B, C, and D. Now, like I said before, we now have systems of equations. Meaning overall that we have negative A being equal to A. And we also have negative D being equal to D. What we also have is, this happens 2 times now, negative B is equal to C and negative C is equal to B, negative 1 is not equal to 0, you can multiply both sides by it. So negative B is equal to C. Now, we can just solve those systems of equations. If we add A on both sides, we have 0 is equal to 2A. If we divide by 2, it's not equal to 0, A is equal to 0. Same spiel here. Meaning, we can conclude that A is 0 and we have that D is equal to 0. Also, we have this condition right here. Now, this is extremely powerful because we know by this condition that we have this system of equations right here, this equality of our matrices. Meaning, if we apply our conditions now to this right here, we are going to get, okay, this thing right here is now extremely important. That we have, okay, A squared is going to vanish, B times C is going to result in negative C squared. Let's put it like this, okay? This is going to give us negative C squared. And also we have A and D are both 0, meaning we are going to get 0 right here. Same spiel here. And also we are going to have D squared is going to vanish, it's 0. And we have negative C squared yet again. I'm going to put it like this. By those newly acquired conditions, we now know that negative C squared, okay, solving a system of equations, once again, is equal to -1. Okay, -1 is not equal to 0, we can cancel it out, meaning C is thus, if we take the square root, nothing but positive or negative square root of 1, leaving us with positive or -1. And bam, 2 solutions to our C right here. And this is extremely good, because now we have all the entries together. We know that C is also negative b, so we have solutions for our entries b and c, meaning our a is thus. On the one hand, a, b, c, d. A and d are going to be 0. Also what we have, on the one hand, here's one solution, okay, we have -1 and 1 right here, okay, just using this condition and this condition right here with the sign changed, or we have the other one, 0, 0, 1 and -1. And with this, we are actually done. This is an extremely important result. We are going to denote this thing right here as being our imaginary unit I. But since we are dealing with matrices, I'm going to define it as being just capital I, okay? This is our imaginary unit I. Now you might ask yourself, well, why do you not call this thing right here the imaginary unit I? Well, it's just like I said in the beginning, we have this ambiguity right here. This just has to do with the fact that this is an orthogonal matrix. And it really doesn't matter which one you actually choose as being your I. It's going to result in the same thing. I, for myself, like to use this thing as the imaginary unit, and this is why we are going to do this. Now, one last remark before we can actually finish all of this off. We have found out a major result. And here's one little fact. We can actually define ourselves real numbers in matrix form. They just look like this, okay? It's just a identity times some scalar a, resulting in a, 0, 0a. There is exactly one isomorphism between 2x2 matrices and the real numbers, and that's exactly this thing right here. Those are just real numbers in matrix form, and those are extremely important because we can add matrices pointwise together. So if we were to add those to our imaginary unit, we could arrive at general complex numbers, and this is what we are going to talk about in the next episode. But up until then, I thank you guys for watching. And there's one more important thing I would like to say after a little cut. I really had to drink something, hence the jump cut. I'm terribly sorry for this. Before we actually call it quits, few last words. So you see, linear algebra is everywhere here. Our whole series is going to rely on linear algebra, and it's not only here, it's like everywhere, okay? In mathematics and physics you find linear algebra everywhere. It's a real powerhouse, be it differential geometry or special relativity. It's just simply everywhere. Matrices, tensors, vectors. It's a really important topic in mathematics, and it's applied mathematics, okay? What we are doing here is applying tools to a problem that we have stated for ourselves. Here's a pro tip. You only learn applied mathematics by doing it, okay? If you exercise like an absolute mad lad. For this reason, I decided to partner up with brilliant.org on this one. And hear me out, okay? They really have a brilliant product. It's not even a bad pun right here, it's really what I mean. Basically, if you are interested in learning how to multiply matrices together, you go on the website, okay, and then you just type in the search bar, for example, linear algebra or matrix multiplication. Then you are going to get to a matrix multiplication exercise sheet. It's going to have a lot of exercises there, and you think about the stuff a little bit, pause and ponder, for example, okay, like Free Blue and Brown would say. And yeah, then you can type in your solution, and then you can actually check if your solution is right or wrong. And they have a lot there, okay? Their exercises range from algebra to electrodynamics and all the way to numerical analysis and of course linear algebra. They have you really covered on their website. And those are really not empty words. I really like to use their product too. It's so much fun working through the exercises, and I'm also still learning stuff, okay? Even me, the Papa, is still learning new stuff. So check their website out. And do you know what's even cooler? Use the link in the description down there, brilliant.org/flammablemess. And the first 200 people to actually sign up for brilliant.org get 20% off the annual premium subscription. It's really good. So if you really like this channel, if you want to see more of this right here and even other series, higher quality videos, I invite you to really check out the sponsors for those videos. They just really help keep the channel alive. And without them, I wouldn't be where I am at the moment. You have seen in the last time more higher quality videos, and really without them, it really wouldn't be possible. I really couldn't spend the time on doing stuff like this. So seriously, check out brilliant.org. They really do a good job with the wiki page, for example, they have right there. It's like a whole new Wikipedia. It's so informative. I have used it before. It's just such a good product, okay? Try out Brilliant. Support the channel if you love the papa. And up until the next video, have a flammable day. Thank you guys for watching. Ciao.
Michael here. How deep is this hole and how much does a prime number weigh?